This is our stress U. Right? When we test it out, that is our U, okay, when it's stretched to fracture or to elastic to plastic, okay? And what we realize is, can someone comment the value of tau max? Okay, so this is our tau max, okay? Right, so can someone tell me, comment on the tau max, please? What can you say about tau max? Anyone? Anyone? Only the two of you. Dajinder and Lux. What can you tell me about tau max? You there? Anyone? Hello? Can you hear me? Or is it the network is down?
We can hear you. It's just that I have no idea.
So what can you say about tau max? Anyone?
Well, we know it's a radius, but we already knew that.
Yeah. So well done, right? So we know that tau max is equal half of the U, right? So if on a table like this, right, you want to use a quench tempered steel. So if this is 690, right, a good approximation for the allowable shear is 690 divided by 2, right? So this will come out to be 345, right? Right? So like for this case, this is 250, right? If you divide by 2, this is what? 125, right? It's a good approximation. Like, oh, here this is 260. If you divide by 2, it's 130, right? It's better to know or have a approximation than not knowing that value, or okay, I'm going to use this material, I need to carry tests. Okay, sometimes you don't have the luxury to carry out tests. Okay, so what you see down here, right, what you see down here is known as the we have a term for it, okay, which you guys will learn more maybe in next week or the week after next. Okay, so this equation over here is known as the maximum, right, shear criteria. Okay, so it is also known as the Tresca yield criteria. Okay, it's also known as the Tresca, and you can see for this case later on, I will explain to you why. You can see Tresca tend to under approximate, right? So if you use Tresca, the values are lower than those that are tested. Okay. Now, where am I going with this? We are using tau max and not the normal stress yield because the magnitude is smaller. That is why from last week's lecture, right, radius of the circle is in this form, which is tau max. So this is the equation that we are going to use, right, to relate to the material behavior, right? Relate to the material behavior over here, right? This is based from material behavior, yes or no, right? To calculate, maybe not maybe, but to calculate the diameter of the shaft. Okay, just an example of application. Okay, so just to write some terms, okay, just to write what I've just said. So tau max will have a lower magnitude when compared to sigma u. Okay, so therefore the design of a transmission shaft is based on shear for ductile material only. Okay. And I want you all to take note is this, okay? Brittle material cannot carry or cannot support shearing stress. Okay, I highlight this. This is important, yeah. Okay, brittle material cannot carry shearing stress. Okay, so we have written an expression over here, right? We have written an expression where tau max is equal to stress average squared plus by the shear xz squared. Okay, and I'm going to call this equation 1. Okay, and then we also know that note, right? We have written this last week. Note that the stress that the center of the circle species our stress average is equal to stress induced by bending moment divided by 2. Okay, so we are going to substitute. Okay, we're going to substitute the stress average into equation 1. Right, so tau max is equal to stress induced by bending divided by 2 squared plus by shear xz squared. Okay, so I'm going to call this our equation number 2. Okay, so I'm going to write out the equation for our moments. Okay, stress due to the moment. Okay, so we know stress due to the moment. The general equation is m y over I, right? And then we have the shear xz is equal to Tc over J, right? Where C is the maximum radius of the shaft. Okay. So now we are going to substitute. Okay, we're going to substitute stress M and tau xz into equation number 2. Then we're going to assemble them together. Okay. So when you assemble them together, you have tau max is equal to my over 2I squared plus by Tc over J squared. Okay, you have this expression, and note that the polar moment of area is equal to twice the second moment of area. Okay, so if you look at any formula, you can see that it's very obvious that the polar moment of area is twice the second moment of area. So when that's the case, it will very conveniently help us, right, to have this expression over here, my. Now we can just put a single j squared plus by Tc over J squared. Okay. So note, okay, another note is that we also know that for my over J to be maximum, right, y must also be equal to c. Yes or no? Which is the radius of the shaft. Okay. So once you get that, you can rewrite this expression over here. So mc over j squared plus by tc over j squared. Okay. Then you can take out everything. Okay, you can take out the c and j. So this will be equal to c over j, and then square root of m squared plus by t squared. Okay. So note, based on our transformation that we have used, okay, so if you look at the previous diagram, okay, right, where we drew our shaft, right, based on this, so we have moment in the y and moment in the z, and the torque is in the x. Okay, so when that's the case, right, if I'm going to copy this diagram across. Yeah, I'm going to copy this diagram across. Right. So for our case, we are going to not have what? Not have the axial load. Okay, we don't have axial load for our case. Okay, because this equation we are proving out will not allow axial loading. Okay. So from this transformation that we can see, we know that m, right? We know that m is equal. So we have moment in the y direction plus by moment in the z direction. Okay, whereas the torque is in the x direction. Okay, so when we assemble everything in, okay, when we include everything into the formula, okay, so the tau max is equal to c over j square root of moment in the y direction squared plus by moment in the z direction squared, then plus by torque in the x direction squared. Okay, so this is the expression that we have. So the tau max over here, this is from material handbook. right? This is the value. This over here, it is from your structure analysis.